Hello! In this video I'm going to go over the equations from the first chapter in Volume 2, Chapter 1 of OpenStax. This is on temperature and heat. So I'm not going to go over any example problems in this video. I wrote down the section number of each section that I'm going to talk about, so I'll just go in order, section 1.1 and then 1.2 all the way up to 1.6. I wrote down the most important equations, so I'll definitely go over those and just kind of sum up each of the sections. So I'm planning on the video taking no longer than 15-20 minutes. Okay, so this chapter introduces heat. So what's different now is, as opposed to Volume 1, is that Volume 1 just talked about work. That was the only way to transfer energy into a system. So work involves a transfer of energy, and so does heat. So heat is a new transfer of energy into a system. And this is going to be summarized in the first law of thermodynamics. Basically all the heat going into an object minus the work done by the object is equal to the change in energy of the object. So we're going to keep track of those two transfers of energy later in the first law of thermodynamics. This chapter introduces something called the 0th law of thermodynamics, which basically is just talking about what heat is before you use it in the first law of thermodynamics. So heat is related to temperature, but they're not the same thing. And this is what the first section is getting at. So if you have two objects and you put them next to each other, or there's some other way that they can transfer heat between each other, and we'll talk more about that in this section. If you put two objects next to each other, heat will flow from the higher temperature object to the lower temperature object. So, which way does energy go? Does it go from A to B or does it go from B to A? And remember, this is not work, so it's not something forcing something else. It's not a force times a distance, which was work. This is just because of a temperature difference. And so we intuitively know kind of what temperature is. You touch something, it's hot. You touch something, it's cold. So if you put those two things next to each other, energy is going to flow from the hot thing to the cold thing. So you could think of this as defining what temperature means. Temperature is something that keeps track of a system, and it's a number where if you put two objects with different numbers, the higher number one is going to go down and the lower one is going to go up. So we haven't really strictly defined temperature, we haven't strictly defined heat, but the 0th law relates the two. Okay. And then the next section starts to explore definitions of temperature. So actually both of these next two sections do that. So I guess let me hold off until 1.3 before we relate temperature to some observable effect that we have. Then we can start to define or set up a temperature scale or something. First, the book is appealing to, and most books do this, appeal to you already knowing something about temperature. And so there are three different temperature scales here. There's Fahrenheit, there's Celsius, and there's maybe a new one for some people, Kelvin. So there's a F here, a C, and a K. So if you have some temperature, so maybe you remember this formula from high school. If you have a temperature in degrees Fahrenheit, and you want to know it in degrees Celsius or vice versa, you could use this equation. So 0 degrees C, so a temperature of 0 degrees C. So we write temperature is 0 and then maybe some units, degrees C. So you might say Tc is 0, and if you plug that into this equation, you would get 9/5 times 0 plus 32. The temperature in Fahrenheit is 32. So this temperature, which was 0 degrees C, is also equal to 32 degrees Fahrenheit. It's also equal to, and it turns out both of these units are not as nice as another one, which is called the Kelvin scale. So if you look at the first equation, you can also say that 0 degrees C is equal to 273 Kelvin. And notice how we don't write degrees Kelvin, we just say Kelvin rather than the other two. Kelvin is what is called an absolute temperature scale, whereas the other two are not absolute temperature scales. So what this means is that there is the lowest possible temperature, and we'll explore why that is when we talk about the ideal gas law, but there is a lowest temperature. And that's not obvious with the Celsius scales or the Fahrenheit scales. Like those scales are negative. Those temperatures can become negative, but the Kelvin scale cannot become negative. You know, you can keep cooling something down and you can get close to 0 Kelvin, but you can't go past 0 Kelvin. So when we have equations, we're going to be, you know, when we have the ideal gas law, you can't use Celsius or Fahrenheit. You have to use an absolute temperature scale. So basically any equation that has T in it, temperature, you have to use Kelvin. Delta T is a little more, you have a little bit more freedom in you could either use degrees Celsius or Kelvin, because they're the same size. Notice how the coefficient here is 1. So degrees Kelvin and Kelvin and degrees C are only off by like an offset of 273. But they have the same step size. So in other words, if you heat something up 10 degrees C, you're also heating it up 10 Kelvin, but you're heating it up 9/5 times 10, or 18 degrees Fahrenheit. So a degree Fahrenheit is smaller than a degree Celsius, right? In order to heat up something 10 degrees Celsius, you have to heat it up 18 degrees Fahrenheit. So a degree Fahrenheit is not as big. And when we say temperature differences are the same in degrees Celsius or Kelvin, that's what we mean. We mean temperature changes are the same, but the absolute temperature is not the same. You know, 0 degrees C is not the same thing as 0 Kelvin, definitely. Okay, let me get rid of some of this stuff. So this page doesn't get too cluttered up here. I guess I can't do this a million times. Okay, so the next thing here is thermal expansion. So if you've seen a thermometer, like a mercury thermometer, you have some liquid and so what am I trying to say? You have like a bulb here and then it goes up, and then you have these markings of temperatures, and there's a liquid level in here, and you read off where it is, and that's the temperature. So the reason this works is that this liquid in here expands the hotter it gets. The volume of that liquid expands, and it expands at a different rate than the surrounding container. So the surrounding container will also expand when heated, but because they're made of different materials, they expand at different rates, and so you can see where the height is of this liquid as a function of temperature. And this helps you create a scale that you can reuse over and over again. So to parameterize how much something grows over temperature, we introduced what's called a coefficient of thermal expansion. So this thing alpha here is a coefficient of, actually, this one's called the linear coefficient of thermal expansion. So taking a look at this equation, I want you to look at the dimensions of both sides. The left has 0 units, 0 dimensions, right, a length over a length. So there's no units, no dimensions on the left, there's no units, dimensions on the right. That means that this coefficient, this constant, a different constant for different materials, so like copper will have its own constant, nickel will have its own constant. That constant has units of 1 over Kelvin. Or you could write it as in terms of one of these other temperature scales. 1 over Kelvin, and then you multiply by a temperature difference in Kelvin, and that gives you the fractional increase in length of an object. So for example, if an object increases in size by 1%, then the fractional increase is positive 0.01. So left side would be 0.01, and the right side would be, it'll, depending on the constant, depending on the material, it'll tell you how much you need to heat the object up in order for it to increase by 1%. So this formula, you might wonder, is this initial volume, is this initial length or is this final length? And the answer is it doesn't matter. As long as delta L over L is much less than 1, then this quantity is approximately the same, whether you plug in the initial or the final value. Because if the fractional increase is much less than 1, then the initial value and the final value are almost the same thing. And so it doesn't really matter what you plug in the denominator. Most of the time we plug in initial, and we'll just decide that we're going to plug in initial here, because a lot of times you know the initial length and you're trying to figure out the final length. Okay, and then one final fact about this is that you can show that as long as these fractional increases are small, then this delta V over V is 3 times delta L over L. So you'll notice right here, see how this is 3 times alpha times delta T. And the reason for that is that, if you have a box, and it doesn't have to be a nice linear dimensions. If you have any object where all dimensions increase by, say, 1%, then that means the volume is going to increase by 3%. And the area will increase by 2%. So we could create another formula that says delta A over A is 2 alpha delta T. So alpha is the linear coefficient of thermal expansion. This thing beta is the volume coefficient of thermal expansion. So for something like copper, both of these exist, but for water, a linear one doesn't exist because water doesn't just go in a straight line. So a lot of times in a table, you'll just see the value of beta for water. Okay, heat transfer and calorimetry. If you took a substance that had some initial temperature, so this was the initial temperature at T equals 0, and you just start heating it up. And you ask, well, what's the temperature of the object? It's going to do a few things. So what happens when you heat up an object? Well, the temperature could go up. So if you're not at the freezing point of the object, the temperature will go up. So pretend you had an ice cube at minus 20 degrees C. So I'm hoping that everyone knows that ice will melt at 0 degrees C, and then water will boil at 100 degrees C. Okay. So if you start off in an ice cube at negative 20 and you start adding heat to it, the more heat you add, the higher the temperature is going to go. This is the relationship between temperature and heat is called calorimetry. And that's the title of this section. So there's 2 main equations for this, and it depends on whether the temperature is changing or not, or whether you're undergoing a phase change. So if the ice is heating up, if you're on this part of the curve right there, then the temperature is changing as you add heat to it, and this is the relationship right here. M is the mass of your sample, and C is something called the specific heat. Again, it depends on the substance. Just like alpha, the coefficient of linear expansion dependent on the substance, so does the specific heat. Water's is actually pretty big compared to most other things. And you can read off the units. So heat, so Q is heat. It's an energy transfer. It has units of joules. So this heat is an energy. Okay, we use the term always as a transfer of energy. So like you would never say that an object has a certain amount of heat inside it. This thing A, you wouldn't say there's a certain amount of heat inside A. There's a certain amount of energy in the form of heat that flowed from A to B or B to A. Okay, so important distinction. Even though it has units of energy, we use it a little bit differently than energy. And that means that, so going back to my original point, that means the units of specific heat are joules per kilogram Kelvin. So the units of C are joules, the SI units are joules per kilogram Kelvin. So you have to multiply by a mass and multiply by a temperature difference to relate Q and the specific heat and delta T. Notice how the value of C, of specific heat, can be different for the solid phase, for the liquid phase, and for the gas phase. So you can have a different coefficient there. One phase of matter might be more efficient at gaining temperature or less efficient, or it might store more energy for every temperature difference. So in other words, the slopes of this graph don't have to be the same for the solid, liquid, and gas phases. Now, sometimes when you add heat to an object, the temperature doesn't go up. And that's this and this right here. So either you're melting or freezing an object, or boiling or condensing, depending on which way you're going, right? If you're going this way, you're melting. If you're going this way, you're freezing. In that case, you're undergoing a phase change, and this is the formula. So notice how there's no delta T in this formula. This is just telling you how much energy you need in order to melt an object or to boil an object. So the L here, so the C was called specific heat, the L is called latent heat. And there's a latent heat of fusion for this one, and a latent heat of vaporization for this one. Okay, so you'll see two different latent heats depending on which phase transition you're talking about. Right? F for fusion and V for vaporization. Okay. So another way of looking at this this fact, or this info, temperature versus energy added or heat added, is in this graph on the left right here. So this graph about phase changes. Now what you're used to is that like a solid will melt first, and then you have to heat the liquid up to boil. So that happens as long as you're at a pressure. So suppose your starting point was right here. So like maybe this is atmospheric pressure and this is the starting temperature of your substance. And what we did in this graph was we heated the object up. So that means go to the right here. So we had to add energy in the form of heat to heat it up. And then in order to cross over this transition right here from solid to liquid, that takes a certain amount of energy, right? That was this right here. So it took some energy to just cross that barrier, and then we had to heat it up here. We had to cross that barrier, and then we could heat up the gas. That's all at a certain pressure. What this graph is saying is that so first of all, it's showing where that melting point is and boiling point is as a function of pressure. But it's saying a lot more. It's saying there's a certain point called the triple point, where actually if you heat something up at a pressure lower than the triple point, you can actually skip the liquid phase entirely. So there's another phase transition called sublimation, where you can go straight from the solid phase to the gas phase. So for water, we don't see sublimation at atmospheric pressure, but we do for something like carbon dioxide. So carbon dioxide has a triple point above atmospheric pressure. So atmospheric pressure would be somewhere down here for carbon dioxide. This is dry ice. So actually atmospheric pressure would be, that stuff would be gas right here. But if you keep cooling carbon dioxide, you desublimate or depose it into a solid. You skip the liquid phase entirely. You would need a pressure bigger than ATM in order to do that. So that's one thing about this graph, is the existence of a triple point. Another thing is the existence of a critical point. So like if you heat a liquid up, you'll definitely notice that you have to pump a lot of energy in to boil right there. As you heat an object up, you'll notice where this phase transition happens. But at a certain point, there ceases to be a strict distinction between a liquid and a gas. So for example, like if you're here and then you go here, the density will change discontinuously. Whereas here, the density, you might get something close to the density of water, and then very gradually you turn into the density of gas. But it won't happen very quickly all of a sudden. So there ceases to be a distinction, as big a distinction between these two phases of matter. And where that transition happens, there's a very specific point where there's the end of the distinction between a liquid and a gas. And so for things out here, we call this a supercritical fluid. Supercritical fluid. So both a liquid or a gas, there's an all-encompassing term for these, and that's fluid. So that's a perfect word for this. If something's a fluid or a gas, but we can't really tell, we call it a super. We can call it a fluid, and then supercritical means something relative to this critical point. Okay, so similar to information here, except showing the pressure dependence for a wide variety of possibilities. And then the last section touches on all the ways that you can transfer energy in the form of heat. And there are three that we talk about in this class. Conduction, which is when you have a hot thing touching a cold thing. Convection, which is fluids moving. So if you had, you had a house and then it's really cold on the outside. So then you have walls of your house. So this is outside, this is inside, and these are walls. I'd say this is winter time. So it's cold on the outside and it's warm on the inside. So the hot air, so the heat, what do I want to say? The air in your walls close to the inside is going to heat up and go up, and the air here is going to cool down because it's going to be next to the outside, the cold temperature out here, cold, hot. And this sets up what's called convection currents in the walls. So these convection currents will carry energy, just by setting up this circle. Fluid will just start moving around like a circular path right here. So you can transport energy that way. So that's called convection. I've just summed it up as fluids moving. This one is probably the most complicated of them to describe, so we don't have an equation for that one, but we still want you to know what it is qualitatively. And then radiation. So you're probably used to this when you see something glowing red hot. So when you heat something up and it starts glowing, it was actually always glowing. It was just glowing in the infrared, which our eyes aren't sensitive to. And when you heat an object up, the hotter you make an object, the higher a frequency it glows at. But there's actually a whole distribution of wavelengths for which something is giving off. The overall result, though, is that depending on temperature, an object is radiating a certain amount of energy per unit time. So these P's in both the conduction and the radiation equation are energy per unit time of energy transfer in the form of heat. So actually, let me talk about I'll talk about the conduction one, and then I'll go back to the radiation one. So the conduction depends on, so you have a hot thing touching a cold thing. So you had a rod, there's hot and there's cold. So it'll depend on the temperature difference between these two objects, that's the delta T. It'll depend on the cross-sectional area of whatever's, so the heat is going across. So when I was talking about the house, it might be the walls of the house. Here it would be the cross-sectional area of this pipe or rod connecting these two. That would be the A. The delta X would be the length over which the heat needs to travel, so that would be this right here. So distance from the hot thing to the cold thing. And then K is a constant depending on the material that is doing the transferring. So like for that rod, it would be whatever the rod is made up of. So this is a thermal conductivity. And has units, whatever it needs to cancel everything out. So let's try and figure this out. So area divided by delta X, that would have SI units of meters on the top. And this is Kelvin on the top. So the K would be 1 over meters Kelvin. And that's not millikelvin, so I might write it this way. Kelvin times meters. Okay, that's conduction. And then radiation depends strongly on the temperature of the object. Okay, so the sun has a surface temperature of about, I think, 5,000 or 6,000 degrees C. So in this equation, you have to use an absolute temperature, so we would have to convert that to Kelvin and then plug it in, but that's a huge amount of energy radiated. And then it also has a huge surface area. So this A is the surface area of the object. This sigma is a constant called the Stefan-Boltzmann constant. It's 5.67 times 10 to the minus 8. 5, 6, 7, 8 is how I remember that. And then the units have to work out so that you're left off with, oh shoot, so up here I said joules per Kelvin meters. This is actually watts. The P is a watt for conduction up here. Sorry about that. And then this one is watts per, so let's see, we need to cancel out the meters squared from the area and then Kelvin to the fourth. So that's the Stefan-Boltzmann constant. And then E is something called the emissivity. E is a number between 0 and 1. And it says how efficient the object is at absorbing and radiating energy in the form of radiation. So a perfect black body is emissivity 1. And if you're not given what this number is, you just assume it's equal to 1. So sometimes you'll see this equation written as sigma A 2 to the fourth without the E right there. So actually, the objects will radiate energy and absorb energy. So you might see this this whole equation written as T radiating minus T absorbing to the fourth. So that's just keeping track of, well, the object's getting rid of energy and it's also absorbing energy, and the difference is what matters. Or you might see it with the indices swapped. So it depends what, for positive, it depends whether you're talking about overall radiated away or are you looking at energy transferred to the object. But this is the basic formula for how much energy is transferred. Okay. That's about the level of detail I wanted to do to go over all of these. Obviously, we're going to do this in more detail, but this should give you enough to get started. And this is not a replacement for the reading at all. This is just in case you're totally stuck and you just need an overview. All right. So we'll do this for each chapter. All right.